Okay, folks, sorry that I couldn't be there today physically. I am a little bit under the weather, so I'm going to record this lecture using Zoom, and I will post this video to our website, course website, so that you can watch the video. And I will try to ask my TA to maybe play this video in the classroom if you are still going to be there on Friday. But if not, please just watch the video offline, okay? And as promised, I think we will try to go over the solutions of the test one. And I'm sure now you have the solution already. So if you have a chance to read through the solutions and compare with your own answers, probably you have already figured out how to do these problems. But if not, let's just go over these 5 questions, and I will just explain how this, how and why the solutions are the way they are. Okay. So let's look at this one by one. The first problem essentially is the conditional probability problem, and we talk about. So in this problem, we have kind of basically 4 events. Actually, if you look at this table, this table here. These are the probabilities. Let's say this is event J, this is event NJ, and this is event, let's say Y, and this is event actually Y complement, okay? Or actually, let's make this a little bit easier, J and J complement, okay? So these are 4 events. So this table pretty much tells you that, for example, this 0.10 is a probability of J intersect YC, okay? And this 0.30 is the probability of J complement intersect Y complement, and so on and so forth, all right? So, okay, so now let's look at the question 1. Given that a person is younger than 25, meaning that we know that as a condition, the event Y happens, what is the probability that they will jaywalk? So essentially, this is asking you to compute the probability of J given Y. As you can see in this answer, you can use a definition of conditional probability, right? The probability of J intersect Y divided by the probability of Y. So J intersect Y is essentially this number, okay, 0.27. That's why I have it here. And then probability of Y, how do we compute that? Probability of Y essentially is the probability of Y intersect J plus the probability of Y intersect JC. Why? Because of the total probability. J and JC form a partition of the sample space, right? So then this is basically 0.27 plus 0.33. Okay, so that's how you get here. And then if you do the division, you get the 0.45. Okay, question number 2, B, complete the tree diagram below, given that Y, which is defined as person crossing the street, is younger than 25. Notice here, it's person crossing the street. It didn't say anything about jaywalking or not. So Y is the same definition as this Y, which is basically all the people who are younger than 25 in this sample space, okay? And the J is defined as just what we defined. People who cross street are is jaywalking. And for this, tree diagram, starting from, the root, we go to Y, meaning we should write the probability of Y, which we already computed here, right? This is the probability of Y, so that's 0.6. And because, Y complement is the remaining part in the sample space, you have a 0.4 here, 0.6 and 0.4 in the first level of tree. And secondly, going from Y, now you know that it's younger than 25. What is the probability of having a jaywalk, right? And we talk about this in the class. This should be the probability of Y and J divided by the probability of Y, okay? So that is the 0.27 divided by 0.6, okay? That's how you get J. And similarly, you can do J complement, and you can do J and J complement here. It's the same thing, okay? So for example, this is the probability of YC J divided by the probability of YC, okay? And you should write out the individual probabilities also at the end, which is basically the 4 numbers in the table, okay? Lastly, determine whether H and J walking on the street are independent. H and J walking on the street are dependent. So this is essentially asking you the event Y and the event J, whether they're independent or not. According to the definition of independent, independent happens when Y intersect J is equal to the probability of Y multiplied by the probability of J, right? So we should just check both sides and see if they're equal. The left-hand side is this probability of Y intersect J. We know that from the table, which is this Y intercept J, which is 0.27. And then probability of Y, we already computed that 0.6. The probability of J can again be similarly computed. The probability of J is essentially looking at the sum of this. So it's 0.37, okay? And you do the multiplication and you compare both sides, they're not equal. So they are not independent, all right? So this is a question number 1. I hope it's clear now. Let's move on to question number 2. Okay, so let's read the problem. A business needs at least one salesperson and one accountant to operate. So this is the definition of the business can operate. You need at least one salesperson and one accountant. You can have more, right? That's the meaning of at least. Okay, so this is the definition of a business can operate. And then it says it typically has 3 salesperson. Okay, it has 3 salespeople and 2 accountants present. Okay, so the business have more than just one salesperson and more accountant just to make sure the business can operate. Now, a salesperson can be sick. This is 0.05, and accountant being sick is 0.10. Okay, these are the known numbers. The question is, what is the probability that the business can operate? Okay, the probability that the business can operate, again, for this question, you should go back to definition to say, for business to operate, we need at least one salesperson and one accountant, okay? So we need to find out the probability that there is at least one salesperson and one accountant, both of which are not sick, okay? Because the probability of a salesperson being sick and the probability of accountant being sick are independent, right? Then we can compute this separately, okay? So let's first look at the probability that at least one salesperson is present. This basically means at least one salesperson is not sick, okay? Then what is its probability? We have to consider the complement of this to compute this in an easy way. The complement of this event is that all the salespeople are sick, okay? For all salespeople to be sick, every single one of them is sick with probability 0.05. Then for all 3 of them to be sick, you have this probability, which is 0.05 to the cubic. And then this is the probability that all salespeople are sick. And 1 minus that gives you the probability that at least one salesperson is not sick, hence it is present, okay? The second is the same thing. The probability of at least one accountant to be not sick is 1 minus the probability that both accountants are sick. So it's basically, okay, I think there misses a 2 here, a square here. So it should be 1 minus 0.1 squared, okay? Lastly, we can compute the probability that the business can operate, which is the probability of at least one salesperson present multiplying the probability of at least one accountant present. So this is the product of the first 2, and you can compute the numbers. Okay, moving on. Question number 3. A dorm has basically 10 resident advisors, a total of 10, okay? On a particular day, there are 2 categories of tasks. First is 3 RAs will be assigned to the front desk duty, 1 in the day, 1 in the evening, and 1 at night. Okay, this is first type of task. The second type of task is that 3 other RAs will be assigned to be on call all day. Okay, so there are 2 different categories of tasks. One is for front desk, and for front desk, noticing that these 3 actually RAs are assigned sequentially. There is an order here because for A to be, let's say, in the day and B to be in the evening, this is different than the assignment of B in the day and A in the evening, okay? So this is basically, you have to consider the order here. For the second task, 3 other RAs will be assigned to be on call all day. And then this task, these 3 other RAs are not really sequential, or the order does not really matter, because ABC to be on call is the same as BCA or CAB to be on call, okay? But ABC to be assigned in the day, in the evening, and at night is different than, let's say, CAB to be assigned in the day, in the evening, at night, okay? So there are 2 different, kind of events here, so we have to be careful. Okay, so let's look at questions. With no other restrictions or conditions, how many unique schedules could the supervisor create? Okay. So with no other restrictions or conditions, meaning that we only have the restrictions and conditions as specified in the problem. This constraints are, you have to have 3 RAs to assign to the front desk and the 3 other RAs to be assigned to be on call. And the first 3 RAs have to be assigned sequentially, and the second 3 can be assigned basically in a batch. The order does not really matter. Okay, so we basically have to compute these 2 numbers separately and then multiply them together. Okay. So this is why in the solution you see this 2 component here. First is basically this is the 3 permutation. Okay. Out of all the 10 RAs, first I pick 3 out of this 10, but I want to pick them in a given order. That's why you have a 10 permute 3 kind of situation. And second, this basically gives you the 3 RAs to be assigned to the front desk duty. Okay. And then after that, you have assigned 3 RAs to the front desk duty. You have 7 remaining RAs. Now you have to select 3 to be on call. And there are 7 choose 3 different possible ways to do that. That's why you have a 7 choose 3 in the second component. Now you have to multiply them together to get the total number of unique schedules. But the question here is to have the unique schedules, okay? So as long as 2 schedules differ in both the front desk group, which is ordered, or the on-call group, which is not ordered, you will consider them different schedule. Okay, here's another thing I want to emphasize. Again, I think I emphasized this already in the class, which is, if you write it out, 10 permute 3 potentially is 10 multiplying 9 multiply 8. And the 7 choose 3 is 7 factorial divided by 3 factorial and 4 factorial, okay? And this is a simple case where you should not just leave the answers like this, because you can do some simplification, right? So 10 minus 9 minus 8, 10 multiplying 9 multiplying 8 multiplying 7 factorial divided by 3 factorial and 4 factorial can be actually simplified, okay? This is why you see that you have this 10 multiply 9 multiply 8 multiply 7 multiply 6 multiply 5 and divided by 3 and 2, okay? That's how you get the final number. This is not a very difficult calculation, so you should do it instead of just leaving the factorials like the way some students do. Don't do that in your future test, okay? Second problem, find the number of schedules that could make that assign 2 of the RAs, Mike and Arjun, to be on call. So okay, so now we're looking at the second group on call. Remember, second group on call has 3 RAs, okay? The first group also has 3 RAs, but they are ordered. Now I'm asking you to make sure that Mike and Arjun are on call. So out of the 3, locations for on call, 2 of them must be occupied already. That's why out of the 10 RAs, you have to also remove these 2, Mike and Arjun, because they are already assigned to on call. Then there are 8 remaining. So you pick 1 out of the 8 to fill this on call duty. That will complete the on call assignment. This is the first part, 8 choose 1. And then for the remaining 7, you pick 3 sequentially. That's the 7 permute 3 situation. And that's how you get the number of schedules, okay? Lastly, I'm asking you to find the probability that Mike and Arjun to be both assigned to be on call. So this is a counting problem. I need to count the total number of different unique schedules. And And then also I need to count the total number of unique schedules that Mike and Arjun to be assigned to be on call. Okay. And you will realize that this numerator is basically problem B, and this denominator is problem A. Okay, so then you can do the math. Again, as I said here, try not to leave it just like this, okay? Do some calculations, simplify the problem. It's not that difficult. And please do make sure you do that in your future test. Okay, I hope this problem is clear. Moving on. Okay, problem 4. This problem has a lot of trouble. I think quite a lot of students have trouble with this problem. So let's look at it, what this problem really is about. So first, we need to read the problem carefully, okay? So let's read the problem. The blood type distribution in the United States follows the following, okay? This is the numbers we have. So for this sentence, basically this tells you that this is the blood type distribution in the United States. So far we didn't say anything about, lab test or, estimation or error. So this is the ground truth. This is really the blood type distribution in the United States, as the sentence says, okay? Then the next sentence says that due to errors in the laboratory procedures, we have that 4% of individuals with type O are mistakenly identified as type A, okay? 4% with type B are mistakenly identified as type A. 10% of AB are mistakenly identified as type A, and 88% of type A are correctly identified, which means they're also identified as type A, okay? Okay, so this is a question. Let's look at the problem. What is the probability that a person selected at the random, will be identified as type A, okay? Noticing here, the question is, this person must be identified as type A. This is not to ask you, this person is indeed type A, okay? So there is a difference here. A lot of the erroneous answers for this problem is that the students mistakenly think that this is asking you, if I randomly select a person, what is the probability that he is type A? No, that's not the question. The question is, what is the probability that he or she is identified as type A? As long as you are identified, that means there is an error, potential error in that, okay? So how do we do this? Because we know that from all these four sentences, they're all giving you the probabilities of different individuals with the true underground blood type. What is the probability that they are identified as type A? So we need to actually use this information, okay? So let's look at, okay, so how we did the calculation below, right? This calculation, for example, are, you're adding up 4 terms. The first term is actually, let's actually write out total probability. Let's say identified as type A. Let's call that, type A. Okay, this is identified as the probability as the type A. Okay, this can be written as the probability of IA given that it's actually let's not use A here. Let's do it according to our answer. So let's do O first. Given that the person actually has blood type O, times the probability of this person indeed has blood type O. And you do that for all the possible ways. IA given B times the probability of B plus IA given AB times the probability of actual AB plus the probability of IA given A times the probability of A. Okay. This is again total probability and conditional probability. Okay. And now we can do the plugin. Okay. The probability of IA given O. This is the probability that the person actually has type O but is identified as A. This is the first sentence. 4% of individuals with type O are mistakenly identified as type A. So this is a 0.4 case. Multiplying probability of the person actually has blood type A. This is the underlying blood type distribution, which is 46%. Okay, you plug in these other things, one by one here. Okay. Right. So and then you do the calculation. All right, so this is the first question. Second question, what is the probability that a person selected at random would be correctly identified as type A? Okay. So this is the probability that the person is basically type A, and he is also selected as type A, identified as type A, right? So this is basically the probability that you have. This is basically asking you the probability that person is identified as A, and he is indeed, of blood type A. Okay. So this is a probability of IA given A times the probability of A. Okay, which is 88% times 41%. Okay, that's question B. Question C, if a randomly selected individual is identified as A, what is the probability they actually have type A? So this is asking the probability that this is asking you the probability that given that he is actually already identified as type A, right? And what is the probability that he actually are type A? So we're asking the probability of actually being type A given that he's identified as type A, right? This is the question. If a randomly selected individual is identified as type A, so you already know that it's identified type A, that's a condition. The probability that is asking that what is the probability that they actually are type A, okay? And we use conditional probability here. This is A union, A intersect IA divided by probability of IA, okay? And then you realize this is from question number B, and this is from question number A. Okay, just plug in. That's how you get these numbers. All right. Lastly, I have 3 randomly selected people, and if they are all identified as type A, what is the probability that exactly one of those 3 people has some blood type other than A? Okay. Meaning that I have identified all 3 people to have type A. Exactly one of them has blood type other than A, meaning that equivalently, exactly 2 of those people have the blood type A. Okay. So how do we do this? Okay. So out of the 3 people, so first of all, this is obviously a counting problem. Out of the 3 people, 2 of them must have blood type A, and 1 of them must not have that blood type A, right? So out of the 3 people, I choose 2, so that's a 3 choose 2 situation. For the 2 people I chose, I have to make sure that they have the blood type A. Okay. So then what I need is to have this probability that given that the 2 people are identified as type A, what is the probability that they are actually having blood type A? And this is exactly the question C, right? That's why you have this probability from here. For these 2 people, they are already identified as type A. This is given. And the question, the probability is what is the probability that they actually are type A? That is basically what we computed for C. And for the second part, this is essentially 1 minus the first part, okay? Because they exactly are of type A, and 1 minus that is that they are not type A. They have a blood type. It has a blood type other than type A, okay? That's how you compute this, okay? All right, so let's move on. This is the expectation and the CDF question for discrete random variables. So let's read the question. You are playing a game where you flip an unfair coin. Okay, notice now here is an unfair coin, and you flip it twice. Okay, if you have basically the coin lands on head with probability P. Okay, this is unfair coin, so P probably is not 0.5. Okay. And then what you know is that if the coin lands on head twice, you win $1. If the coin lands on tail twice, you win $2. If it lands on head once and tail once, you lose $2. Okay. So this random variable is $1 or $2, or let's write here minus $2. So $1 is when you have head, head, $2 if you have tail, tail, and minus $2 is you have head, tail, or tail, head. Okay. And now I define a new random variable x to be the amount of you win when you play this game exactly once. So you can okay. So think about it. What is the range of x? X can be $1, $2, or minus $2. Okay. And now you're given the CDF. So let's look at this plot, right? First of all, we have taught in the class, you need to look at these possible values. These are the range of x. So this is -2, and this is +1, and this is +2, and this is +2. Okay, so you have basically -2, 1, and 2. That's exactly what I just said. These are the range of x. Then correspondingly, we taught in the class that you should look at this step sizes, right? These numbers are the corresponding probabilities of this random event. Okay, so the probability of x equals -2 is going to be exactly this number, which is 0.375. And this is the probability of x equals 1, which is, I think this number is 0.9375 minus the bottom value here, which is 0.375. Okay, and this is the probability of x equals 2, which is 1 minus 0.9375. Okay, so this is how you read the CDF. We taught this in the class. Okay, so now let's go to look at the problems. First question, find the probability you win $1, which is basically the probability of x equals 1. Okay, that is what we computed here. So you have to, this is what you do here. Okay, you get the result, which is good. B, if you play this game over and over, how much would you expect to win each game on average? This is the definition of expectation, right? Expected value. So we know a few things, right? We know x equals -2 to be, 0.375. X equals 1 is something we have computed here above, right? This is the number we computed. And x equals 2 is, as I said here, right? 1 minus 9375. So this is 0.625. Okay. So you have these 3 probabilities. Now the expectation of x is the corresponding x value multiplying their probabilities, and then sum them together, right? Sum all these 3 things. Okay. -2, +1, and +2. Okay. So that's how you get the results. Lastly, find the probability P. Okay. You can just use this single one, right? The event of winning $1 is exactly the event of having 2 heads. Okay. So probability of 2 heads, which we know that the probability coin lands on the heads with probability P. So this is basically P squared. And this is exactly the probability of x equals 1, right? So this is basically because x equals 1 is head, head. Okay. So we can solve this equation, okay? Because we know what x equals 1 is, which is based on, here, 0.5625. Okay. So that's how you do the computation and get the results. Okay, with that, I think I'm done with the exam, and I hope this explanation is clear and useful to you. Obviously, after you read this solution, you should already know pretty much the correct answers. But hopefully, this video gives you some additional information. Hopefully, that's going to be useful. So with that, I will conclude today's lecture. And sorry again, I'm a little bit under the weather, so I have to do this video to present my lecture for Friday. I hopefully will see you on Monday. Okay, take care.